All right, let's learn about momentum conservation in systems. We're going to draw a collision systems model and calculate the total momentum. So this is how we do it. We first got to know what a system is. And remember, the goal of science is to understand the universe. Here's the universe, and if we want to understand it, that's just too big. So we cut out a little piece, and that's what a system is. It's a portion of the universe that we want to make sense of. And we examine and analyze the pieces of the universe that are in those boundaries. We can look at what goes into the system and what goes out. Some inputs in physics are things like forces. If you push on objects in a system, or matter might go in, and energy. And there's also outputs in physics as well. Energy and forces and matter can leave the system. So we use a systems model to examine phenomena, things we want to understand. And here's one phenomenon. Curling is this weird sport in the Olympics where they slide these stones on ice on a frictionless surface, and they try to land it on a little target. And they collide with one another. And that's a perfect way to study collisions, is to look at this phenomenon. And we got this great simulation here. And we could use this simulation to collect some data. And that's what we'll do. We've got these curling stones. We're going to send the red one to collide with the yellow one. Boop. And there's some momentum changes going on. And so we're going to examine this system of objects here. So we'll use this template to model that system. The first thing we want to do is describe the phenomenon, and it's just that the red curling stone collides elastically. That just means they bounce off at one another with the yellow stone. The next thing we want to do is define the boundaries. Now, this boundary is a closed system. What that means is that we're not going to consider the ice scraping on the stone. We're not going to think about the earth pulling on the stone or the initial push. Our system happens right in the moment where the red is starting to move towards the yellow stone, and then they connect, and then that's when our system ends. So that's our boundary. It's a closed system. Good. So we want to next thing we want to draw and label the components. So we have a red stone and we have a yellow stone. They're drawn, and we want to identify the relationships that they have with one another. So the red stone hits the yellow stone, it applies a force, and the yellow stone hits the red stone. That's a reaction force. That's a force pair, Newton's third law. For every action, there is an equal and opposite reaction. Now we want to identify initial conditions. So what were the initial conditions there? So if I start over here, I click on the red stone, it's moving at 1.5 meters per second, and we have their masses as well. So that was the initial conditions before they collided. Let's write those in. So the mass of the initial mass for the red, 24 kilograms, the initial velocity, 1.5, and we write down the same thing for the yellow. The next thing I did is I calculated the mass times the velocity to get our momentum. And I did that for both stones. And I calculated not the momentum for just the red and just the yellow, but for both the red and the yellow together as a system. And I get the initial momentum for the system. And that equals 36 kilograms meters per second. So we want to determine the values for the system as a whole. And all we do is we add the momentum of the red stone plus the momentum of the blue, that should say yellow stone. Okay, identify final conditions. Okay, so now if we look at our data here, it tells us some final velocities. The final velocity of the red, it's moving at 0.30 meters per second, and it gives us data for the yellow, which is nice. So they collected some data for us, and so we'll write that down and do the same thing. Mass, velocity, and this is little f is for final. And we're going to calculate the momentum again. I'm going to use my calculator to multiply those numbers together. Same thing for the yellow. And then same thing, we're going to add the red final momentum plus the yellow final momentum to find the total final momentum of the system. And we get 36, that same number that we got before. That's kind of interesting. So that's how we use a systems model template to really draw all the stuff in the system. The last thing is to identify any inputs. Well, in this case, there are none. We didn't add any momentum to the system. So there's 0 kilograms meters per second of momentum added. Same thing with the output. 0 kilograms meters per second, no momentum left the system, and the total change in momentum of the system was 0. So this is us all filled out here. Notice in orange here, we have the initial momentum of the system, 36. The final momentum of the system, also 36. There was no change when we created the boundaries of the system. Kind of interesting. That is a big idea in physics called the conservation of momentum. And that states that the total momentum of a system cannot change. The total momentum of the system before the collision will equal the total momentum of the system after. The change in momentum for the system will always be 0 kilograms meters per second. Now, objects versus the system. Remember that an object's momentum will change. Here's the Yellowstone, boom, it gets hit, its momentum does change. But the system's momentum will not change. That's called the conservation of momentum. Momentum is conserved, meaning it's conserved just means it stays the same. You want to conserve nature, you want to keep it the same. Good. Some limitations. Any external force, like an input, that's going to change a system's momentum. So in this case, the momentum of the system will not be conserved. It will change if you consider the ice exerting some force of friction on that stone. So that's some limitations. All right, here you have it. This is how to create a systems model, and y'all will be creating many of these on your own. So good luck.